Now I'm going to introduce you to Stokes Theorem. And I'm going to do so by having us evaluate a line integral, because Stokes' theorem involves line integrals of vector fields. So here I have a vector field, and we're going to evaluate this line integral over this path shown in this graph. Now this path is a positive orientation. It goes along C1, C2, and C3. And what I've done is I've parametricized each of those lines. So what we have to do now is we have to evaluate the line integral along each one of those paths. Okay, so we have to be careful because there's lots of opportunity to make a mistake, and I want to just carefully go through this, and this would be a bit of a review on how to evaluate line integrals. So first of all, we'll look at C1. Now C1, I've defined the path to be this way. It's going to be 3 minus 3t I plus 3t j. And then you can say plus 0k. I didn't put that in originally, but you could say plus 0k. Plus 0k. Now, you'll notice that, and t goes from 0 to 1. Now, you'll notice when t is 0, I get the point 3, 0, which is this point right here. And when t is 1, I get 0, 3, which is that point right there. So that is a good parameterization for that curve. Now, here's what I want to do. I want to convert my vector field expression here, and so that everything is in terms of t. So we have negative y squared. That's the x part of it. Now negative y squared is going to be negative 3t squared. So that's going to be the x component. Now, comma, let's see what's next. I have z. Z is equal to 0. So that's the y component. It's a little bit confusing. And then x that's the last component there, is 3 minus 3t. Okay, 3 minus 3t. So now we're ready to write, our integral, 0 to 1. And I've got this. I've got negative 9t squared, comma 0, comma 3 minus 3t. And I'm going to dot that with the derivative of this thing, the derivative of that. So let's see here. The first part is negative 3. The y is 3, and the z is 0. Okay. So notice I have the negative 3 from this, the 3 from this, and then the 0. Now all we have to do is do the dot product and evaluate this. And here's what we get. It looks like this is just going to be 27t squared dt. Or, if we evaluate it, we get 27 over 3t cubed from 0 to 1, and that's just 9. Now, what I want to do, I want to go back and be sure I remember this. So I'm going to put a little box around it, because remember, in finishing up this problem, we're going to have to add up all of these, the integral that we got from C1, C2, and C3. We'll have to add those up. Putting them together will give us the entirety of the line integral. Okay, now let's look at C2. Okay, so here's C2. Okay, so here we go. Now for C2, recall we had this one. We had r of t is equal to, now there's no x, but the y was 3 minus 3t, and then we had 6t. Okay, so that's what we had. 0, 3 minus 3t, and 6t. And now, remember also, now what I want to do now is convert the vector field to be in terms of t. So here I go. I've got the first part of it is negative y squared, and that's going to correspond to negative 3 minus 3t squared. And then I had z, and z in this case is 6t. And then finally x on the end, the last term would be 0. Okay? So it looks like we're ready to write our integral, and I chose it, so I parametricized everything so that t would always go from 0 to 1. So we don't have to worry about that. Now, so let's see what we've got here. We've got negative 3 minus 3t squared, 6t, and 0. And we're going to dot that with 0, 3 minus 3t, and 6t. Whoops. dt. Now, actually, I did make a mistake here, didn't I? Remember, this is the derivative. So this over here has got to be the derivative. Okay. So we take the derivative of this would be negative 3, and the derivative of this would be 6. Now we're ready to integrate. So I took the derivative of 3 minus 3t and got negative 3, derivative of 6t, and I got 6. So let's see what this looks like now. If we go ahead and find the dot product, we're going to, okay, these ones will be 0, and this will be 0, and here we just have negative 18t and we're ready to integrate. So here we go. We've got this. We've got negative 18 over 2t squared from 0 to 1, and that's negative 9. So that takes care of C2. Now look what we've got. We've got C1, which was 9. C2 is negative 9. So that's where we stand so far. We put a box around that, and then we're ready for C3. Okay, that will finish up all the integration that we have to do, and then we just add everything. Okay, so on this one, on C3, recall that we had this one. We had 3t, and then 0, and then 6 minus 6t. Okay. Now, so remember that corresponds to this last curve up here. This curve goes from 0, 0, 6 to down here to 3, 0, 0. So let's see if that works. If we put in a 0 here, we got 0, 0, 6. If we put in a 1, we got 3, 0, 0. So that works. So just to verify it again. Now, last time I forgot to do the derivative, so let me go ahead and take care of that now. This is going to be 3, 0, negative 6. Okay. Okay, now let's rewrite the function then. I've got negative y squared. Now, so I'm going back now and rewriting the vector field. That's what I'm doing. So I've got negative y squared. Well, that's 0. And then I've got z is the middle term. And z is going to be 6 minus 6t. And then finally on the end, x, and that's equal to 3t. So it looks like we have this. It looks like we have 0, 6 minus 6t, and 3t. Okay, because this is negative y squared. This is z. And then this is x. And now we're ready to set up our integral. So here we go. We've got the integral from 0 to 1. And this is going to be 0, 6 minus 6t, 3t. And I'm going to dot that with 3, 0, negative 6. Now, let's see what happens. This is 0, this is 0, and we just get 0 to 1, negative 18t, which is negative 9t squared, which is negative 9. Okay. Now, so here's our integral. Finally, when we get through with all this process, look what we've got here. We've got 9, there's 9, negative 9, and finally negative 9. So our integral is 9 minus 9 minus 9, which equals minus 9, negative 9. So what we've done there is we have evaluated that line integral over those curves. That's what we've done. Now, that was kind of time-consuming because we had 3 curves, and what we'd like to do is figure out a shorter way. And that shorter method is going to involve the curl. So let's remind ourselves about the curl. The curl of f. Okay. So we want to find the curl of f. Now remember, recall if you've got a vector field, you've got x, y, z. The vector field, if you have this vector field and you want to talk about the curl is going to be I, we set it up this way, and then we have the derivative operator, partial with respect to x, partial with respect to y, partial with respect to z. And then here, now let's suppose, let me finish this up a little bit. Let's suppose this is m, n, and p. Drag this down. Okay. What we would do is we would put an m, n, and p here. And this is going to give us the curl. We work this just like we would if we were finding the determinant. So in our particular example, we do have a vector field here. We have a vector field, and we'll look at we'll use it. We'll find the curl of our vector field. We've got y, negative y squared, z, and x. Okay, now here I go. I'm going to find the curl now. Now remember, an alternative way to write that is this. So we're finding the curl of this function, of this vector field. We would have I, j, k. And then I'm going to put partial with respect to x, partial with respect to y, partial with respect to z. And then we put these values in here. Negative y squared, z, and x. This is our curl. Okay. Now let's see what this turns out to be. Okay. Now, first of all, I'm going to say, okay, the partial of x with respect to y, taking care of this one, and that's 0. So here we go. We got I, and here's 0, minus 1. Okay, so we did that one. Now, minus j. Okay. Okay. Now we're ready to take care of the j. The partial with respect to x here, that's just going to be 1. And then minus 0. And then plus k. Now we're ready for the last part of it. We're saying, okay, partial with respect to partial with respect to x of z is 0. Now, this one, the partial with respect to y, is going, so this is going to be minus a negative 2y, like that. So it looks like what we have here is we have I, well, negative I, minus j, and then plus 2yk. Or I like to write it this way. Okay, the next thing I want to do is, so I'm gonna remember that I've got this setting over here. Okay, so I'm going to use this vector here in a minute. I'm going to use this curl here in a minute. But what we want to do is we want to remember back to the surface that we had at the beginning. Remember, we had these C1, C2, and C3, and what they did was they enclosed in this surface. And the surface, this is the first time we really referenced this, was 2x plus 2y plus z equals 6. And let's just go back and remember this surface right here. So this is like that's where this plane is intersected by these three lines. Okay, so let's look at that surface. And here's what I want to do with that surface. I want to say, I want to get a g of x, y, z, and write it in the form that we've been using. I'm going to have 2x plus 2y plus z minus 6. And then what I want to do is I want to find the gradient. Okay, now remember how we find the gradient. This is going to be 2, 2, and 1. Right? Partial with respect to x, partial with respect to y, partial with respect to x, partial with respect to y, and partial with respect to z there. Okay. So now we've got those two things. Now, here's what I want to do. I want to look at this particular integral where we've got f dot n ds. Now, this is a surface integral. So we've recently worked with surface integrals, and we know that this right here is the n. So now let's see if we can put everything together. Here's what we've got. We've got the surface integral, and here's what I'm going to do. I'm going to go up here back to, back to the vector right here, -1, -1, 2y. Okay, so let's do this. Let's do -1, -1, 2y. So I'm kind of, this is like playing the role of my vector field. Okay, so this is the curl of f. Okay, so you can kind of match it up. Now I'm going to dot it with this n, 2, 2, 1, and then I've got dA here. So I'm integrating this over a region. So this should look familiar. This is the way we've dealt with surface integrals before. But this is what we've got. So, okay, now let's continue on. So we know how to deal with this. What I need to do is set some bounds. Okay. Now remember the bounds that we get. We had this curve, right? Whoops. Let's go back here and look. We had 2x plus 2y plus z equals 6. Okay, so we'll use that to get our bounds. Okay, so here we go. We have 2x plus 2y plus z equals 6. Okay. And we're trying to get the bounds for our integral, so I'm just going to let z be 0 and divide through by 2. So I get x plus y equals 3. So now let's do this. If we integrate with, so now let's set up our integral. We're about ready to set up our bounds. This is going to be -2 minus 2 plus 2y. And now I have to set up my bounds. I think I'll integrate with respect to x first and then y. So here I go. With respect to x first, I get that x, solving for x goes from 0 to 3 minus y. And you can see that from looking on here. X is going to go, you fix a y, and x is going to go from 0 up to here. And then y just goes from 0 to 3. Okay, now let's see what we got here. So if we go ahead and clean this up a little bit, get ready to integrate, we get negative 4 plus 2y dy. Okay, now we're integrating with respect to x first. So here we go. We've got 0 to 3. And this is going to be negative 4x plus 2xy from 0 to 3 minus y dy. Okay. Now I go ahead and put in the 3 minus y. So let's see what we get when we do that. Okay, so this is negative 4, 3 minus y, plus 2, 3 minus y times y dy. Okay, continuing on, let's see what we got. Just clean it up a little bit. We've got negative 12 plus 4y. You just have to be very careful here. Now, plus 6y, and then plus 2y squared. This is dy. Okay, and I guess this should be negative 2y squared. There we go. Okay, now let's see. We can clean it up a little more. 0 to 3, and this is going to be negative 2y squared plus 10y minus 12. Okay, now continuing on. Now it's really easy. So we've got negative y cubed plus 5y squared minus 12y. And we're going from 0 to 3. Okay. Now we just put in a 3. Okay. So we've got negative 3 cubed plus 5, 3 squared minus 12 times 3. Now look at me. I messed up here again. This is actually this right here should be negative 2/3. Okay, so I've got 2/3. There we go. And I think that fixes it. I think that should take care of all of it. Okay, so now let's see what we've got. This is going to be 27 divided by 3 is 9, so this is negative 18 plus 45 minus 36. Okay. So this is going to be negative 18 plus 9 equals negative 9. Now what you'll notice is that when we went through this process, we got the same thing that we got when we evaluated the line integral. In other words, we evaluated this surface integral, this one right here, and we got the same thing that we got when we went through the process of evaluating the line integral. Now this brings us to Stokes' theorem. So let's take a look at that. Here's Stokes' theorem. Okay, so it says let S be an oriented surface with a unit vector normal, bounded by a piecewise smooth, simple, closed curve, C, with a positive orientation. Now, remember, I'll talk about that in a minute. If F is a vector field whose component functions have continuous first partial derivatives on an open region containing S and C, then this is true. This is what we want to focus on here. We're saying this line integral right there can be evaluated using this surface integral. Now, remember, it says that it's oriented in the positive direction. sometimes you might have a little bit of difficulty when you're dealing with these three-dimensional things, or when you're dealing with a surface and you're trying to determine if the curve is positively oriented. Well, remember that here's a helpful illustration. If you think about the normal coming out of the surface, heading outward, and you imagine grabbing the normal with your right hand, well, your fingers will, if the curve is oriented positively, your fingers will point in that direction. So notice this one's fingers. It's pointing in the direction of the curve. Okay, if the curve was going the other way, it wouldn't be pointing in that direction. So this is Stokes' theorem. And now let's just look at an example, a real quick way that we can use Stokes' theorem, because before we were kind of showing how it worked. Now let's just see how in practice you would go through Stokes' theorem very quickly. There I go. Okay, so here let's try this. Let's try an example. So we've got, let's suppose that we have a vector field. Let's say, okay, x, y, and z, and let's suppose it equals, let's say 4xz and y, and then 4xy. And let's suppose that the surface is generated by this, 9 minus x squared minus y squared. And we'll say that z is greater than or equal to 0. Okay, so what we want to do is we want to use Stokes' theorem to evaluate this integral. That's what we want to, in other words, we've got this line integral, we want to use Stokes' theorem. So first thing I need to do is I need to find the curl. Okay, so here we go. Here's the curl. And the curl, remember, partial x, partial y, and partial z. And then let's see what else here. We've got 4xz, y, and 4xy. So let's just make sure that's correct. 4xz, y, and 4xy. Okay, now let's go ahead and find that curl. So here we go, the partial with respect to y. So here we go, I, and that's going to be 4x. Period. Because this one right here, this one partial with respect to z will just give you a 0. So it looks like we have a 4x. Minus j. Now, we've got partial with respect to x, so this is going to be 4y minus 4x. Because we take the partial with respect to z of this thing. Now finally, plus k. Okay, so we've got the partial with respect to x, that's 0. Partial with respect to y, that's 0. So now it looks like we've got our curl. Our curl is going to be 4x, and this is going to be 4x minus 4y, and then 0. Looks like that's going to be the curl. Now we need the normal vector. So let's see about getting that. We're going to take, remember, g of x, y, z is equal to, I think we said it was, z was equal to 9 minus x squared minus y squared. So this is going to be z plus x squared plus y squared minus 9. And then we get the gradient And we're going to get partial with respect to x, which is 2x, partial with respect to y, and then 1. So there's our gradient. And now we're ready to plug into Stokes' theorem, because remember Stokes, we have the curl of f dot n and ds, and we've got the component parts. The two things we needed the curl and the normal. So let's see here. Now we're ready to set this up. The curl was 4x minus 4y. And we're dotting that with 2x, 2y, and 1. And then we have dA over here. Now continuing on, let's see if we can clean this up a little bit. We have, okay, if we dot product this, we're going to have 8x squared plus 2y, 4x minus 4y, and then 0, of course. And now we're ready to set up the bounds. So let's go ahead and set up the bounds. So here we go. We've got let's see here. We've got 8x squared plus 8xy minus 8y squared. And now we just need to determine the bound. So I think what I'll do is I'll just start with, now remember we had x squared plus y squared equals 9. So if we're integrating with respect to y first, we're going to have negative 9 minus x squared, and then 9 minus x squared up here, and then 0 to 3 for the x. And when we integrate this, when it's all said and done, we should get a 0. But that's an example of how you use Stokes' theorem to evaluate a line integral. You need the curl of your vector field, and then you need your normal vector. You put those things together, and then you have a surface integral that you can use to evaluate or come up with a value for the line integral.